Now we are going to see few theorems on inverse of a matrix. The first theorem states if a square matrix has an inverse, then it is unique. That means there is only one inverse for a given square matrix A. Let A be a given square matrix of order n. If B and C are two inverse, then what is the condition? AB is equal to BA is equal to I if B is the inverse of A. Similarly, AC is equal to CA is equal to I if C is the inverse of A. Now, we can write C as C into I. Now, in the place of I, if we replace AB, it is going to be C into AB. The same thing, using associative property, it can be written as CA into B. Now, CA is nothing but I. So, this is equal to IB. IB is equal to B, which indicates C is equal to B. Therefore, the inverse of a square matrix is, therefore, the inverse of a square matrix is unique. A is a square matrix of order n, then A inverse exists if and only if A is non-singular. So when we say if and only if, we should prove two cases. The first case, let us take A is non-singular. Then A inverse is equal to A inverse A is equal to I. By the property of determinants, modulus A inverse determinant of A inverse is equal to determinant of A inverse A is equal to determinant of I. So here this can be written as determinant A into determinant A inverse is equal to determinant A inverse into determinant A is equal to determinant I. Now this determinant I value is nothing but 1. Hence A inverse exists. Suppose A is non-singular. A is non-singular. That is, determinant A is not equal to 0. We get A into adjugate of A is equal to adjugate of A into A is equal adjugate of A into A is equal to determinant A into In. So here we can say dividing throughout by determinant A. You get A into 1 by determinant A into adjugate of A is equal to 1 by determinant A into adjugate of A into A is equal to 1 by determinant A into In. So determinant A gets cancelled. So you are going to get this value is equal to 1. So which indicates the property. Hence the inverse, therefore A inverse is equal to 1 by determinant A into adjugate of. The next theorem states, if A is not singular, then determinant A inverse is equal to 1 by determinant A. Now here, let A be non-singular. Then A inverse is equal to A inverse into A is equal to I. Now this is one. So now on taking determinant on either side, determinant A inverse is equal to determinant A inverse A is equal to determinant I. By the product rule of determinants, determinant A into determinant A inverse is equal to determinant A inverse into determinant A is equal to 1. So A inverse is equal to this gives you determinant A inverse is equal to 1 by determinant. The next property says A transpose the whole inverse is equal to A inverse the whole transpose. Once again from 1, A inverse from 1 we get A inverse. A inverse is equal to A inverse into A is equal to I. Now taking transpose on either side. A inverse the whole transpose is equal to A inverse A the whole transpose is equal to I. So this can be written as A transpose reversal law. A transpose A inverse the whole transpose into A is equal to A transpose into A inverse the whole transpose is equal to I. So cancelling A transpose on either side, you are going to get, hence by the reversal law of transpose we get A transpose the whole inverse is equal to A inverse the whole transpose. Now the third property is lambda A the whole inverse is equal to 1 by lambda into A inverse, where lambda is a constant. So here from 1 we get A inverse is equal to A inverse A is equal to I. Now multiplying by the constant lambda, you get lambda A, multiplying and dividing by lambda. Lambda A into 1 by lambda A inverse is equal to 1 by lambda A inverse into lambda A is equal to I. Therefore, by the reversal law, lambda A, the whole inverse, is equal to 1 by lambda into A inverse. The next theorem is on left cancellation law. If A, B, C be the square matrices of order n, if A is non-singular and AB is equal to AC, then B is equal to C. The first condition is A is non-singular. If A is non-singular, then A inverse is equal to A inverse A is equal to I. It is given AB is equal to AC. This is given. So post multiplying by A inverse on either side, you are going to get A inverse AB is equal to A inverse AC. Again, A inverse A into B is equal to A inverse A into C. Cancelling, left cancellation law, cancelling A inverse on either side, this implies B is equal to C. The next theorem we are going to say is on right cancellation law. Let A, B, C be square matrices of order n. If A is non-singular, BA is equal to CA, then B is equal to C. Given A is non-singular, which implies A inverse exists. Therefore, A inverse is equal to A inverse A is equal to I. We are given BA is equal to CA. So, BA is equal to CA given. Post multiplying by now we have to post multiply by A inverse on either side. You are going to get BA into A inverse is equal to CA into A inverse. By associative law, we can say B into A inverse is equal to C into A inverse. Now you know A inverse is equal to I. So which implies BI is equal to CI gives you B is equal to C. The next theorem is on the reversal law for inverse. You have already learnt the reversal law for determinants. If A and B are non-singular of the same order, then the product AB is also non-singular and AB the whole inverse is equal to B inverse A inverse. If A and B are non-singular, A inverse and B inverse exist and they are also non-singular. So, if A is not equal to 0 and B is not equal to 0, implies A inverse and B inverse exists. AB, A is not equal to 0 and B is not equal to 0 also implies AB is not equal to 0. Therefore, AB is non-singular using the determinant property. Determinant AB is equal to determinant A into determinant B. Now, we can find the product of AB and B inverse A inverse. So AB into B inverse A inverse. AB into B inverse A inverse can be written as A into B inverse into A inverse using the associative property. This can be written as A B inverse is I into A inverse. This is equal to A inverse. This is equal to I. So AB into B inverse A inverse is equal to I. Similarly, B inverse A inverse into AB is equal to B inverse into A inverse A into B. We are using the associative property. Next line can be written as B inverse A is equal to I into B. So this is equal to B inverse into B. This is equal to I. Hence, from 1 and 2, AB into B inverse A inverse is equal to B inverse A inverse into AB is equal to I. Therefore, B inverse A inverse is the inverse of AB. The next law is the law of double inverse. If A is non-singular, then A inverse is also non-singular, and A inverse, the whole inverse is equal to A. First we should prove A inverse is non-singular, then we need to prove A inverse, the whole inverse is equal to A. If A is non-singular, implies A inverse exists. Therefore, we are going to get determinant of A inverse is equal to 1 by determinant A. See, A is non-singular. Therefore, determinant A is not equal to 0. Therefore, A inverse is also not equal to 0. Implies A inverse is non-singular. To prove A inverse, the whole inverse is equal to A. We know that A inverse is equal to A inverse into A is equal to I. This gives you A inverse is equal to I. So A inverse, the whole inverse is also equal to I. Using the reversal law, we are going to get A inverse, the whole inverse into A inverse is equal to I. Post multiplying by A, we get A inverse, the whole inverse into A inverse into A is equal to I into A. So A inverse, the whole inverse into A inverse A is equal to IA. So A inverse, the whole inverse into, this is going to be your I. This is equal to IA. Implies A inverse, the whole inverse is equal to E. Next, we are going to see if A is non-singular square matrix of order n, then adjugate of A inverse is equal to adjugate of A inverse, that is equal to 1 by determinant A into A. We are given A is singular, non-singular. So if A is non-singular, A inverse exists. We know that A inverse is equal to 1 by determinant A into adjugate of A. From this we get adjugate of A is equal to cross multiplying determinant A into A inverse. Now, we need to find out adjugate A, the whole inverse. So, before that, let's find out what is adjugate of A inverse. So, replace A by A inverse, replacing A by A inverse in 1. We get adjugate of A inverse is equal to determinant A inverse into A inverse the whole inverse. Now A inverse the whole inverse is A. Therefore, determinant A inverse into A. So, by associative property, this can be written as A into determinant A inverse. This is adjugate of A inverse. From 1, adjugate of A, the whole inverse is equal to determinant A inverse, the whole inverse. So this is equal to determinant A inverse into A inverse, the whole inverse. This is equal to 1 by determinant A into E. This is equal to adjugate of A, the whole inverse. Now from 1, 2, and 3. Now from 1, 2, and 3. We get adjugate A, the whole inverse is equal to, see this value is 1 by determinant A into adjugate of A. So here again, this determinant A inverse is nothing but, this is equal to 1 by determinant A inverse is nothing but 1 by determinant A into A. So from 1, 2 and 3, we get adjugate of A is equal to adjugate of A inverse is equal to 1 by determinant A into A. The next property is a determinant of adjoint of A is equal to determinant A the whole power n minus 1. We already know that A into adjugate of A is equal to adjugate of A into A is equal to determinant A into unit matrix of order 1. Taking a determinant throughout this equation. So we get determinant of A into adjugate A is equal to determinant of adjugate of A into A is equal to determinant of determinant A into I power n. So this can be written as determinant of A into determinant of adjugate of A is equal to determinant of adjugate of A into determinant A is equal to determinant of determinant A in. So this is equal to A power n. So here this value is going to be determinant A into adjugate of A is equal to A power n. Determinant A power n. Okay. So you wanted to find out the adjugate of A value. So this is equal to determinant A power n divided by determinant A. So this is equal to determinant A power n minus 1. So adjugate of A is equal to determinant A the whole power A minus 1. Determinant of adjugate of A is equal to, see throughout we have adjugate of A. Determinant. Determinant A into determinant adjugate of A is equal to determinant A power n. Therefore, determinant of adjugate of A is equal to, take this down, so you get divided by determinant A. So adjugate of A is equal to determinant A power n minus 1. Hence, we prove a determinant of adjugate of A is equal to determinant A the whole power n minus 1. To prove the next property, adjugate of A is equal to determinant A power n minus 2 into A. Let us take for any non-singular matrix B into, for any non-singular matrix B into adjugate of B is equal to the same rule. B into adjugate of B is equal to adjugate of B into B is equal to, you are going to get determinant B into I. So now in this formula, if you are going to replace B as adjugate, B is equal to adjugate of B. Now replacing B by adjugate of A, we get adjugate of A into adjugate of adjugate A is equal to determinant adjugate of A into IN. So this is going to be adjugate of A value is equal to, we have found out to be determinant A the whole power n minus 1. So this is equal to determinant A the whole power n minus 1 into n. So adjugate 1 by determinant A into whole power n minus 1 into adjugate of adjugate A. Now, it's enough we replace only then. So if we write here adjugate of A is equal into adjugate of adjugate A is equal to determinant A the whole power n minus 1. Now pre-multiplying by determinant A, we get A into adjugate of A into adjugate of adjugate A is equal to determinant of A power n minus determinant A into determinant of determinant A power n minus 1. So this value is going to be A into adjugate of A. A into adjugate of A is equal to determinant A. So determinant A into adjugate of adjugate A is equal to determinant A power, we are supposed to A power n minus 1. Therefore, adjugate of adjugate A is equal to determinant A power n minus 1 divided by determinant A. This is equal to determinant A power n minus adjugate A. And pre-multiplying by A here, this is there. The next property is adjugate of lambda A is equal to lambda power n minus 1 into adjugate of A, where lambda is a non-zero scalar. We know that adjugate of A is equal to determinant A into A inverse. Suppose this is equal to determinant A into A inverse. Replace A by lambda A. So we get adjugate of lambda A is equal to adjugate of lambda A is equal to determinant of lambda A into lambda A the whole inverse. So this is equal to determinant of lambda A value as the A is of matrix order n. The value of determinant lambda A will be lambda power n into determinant A. This is 1 by lambda into A inverse. So this is equal to lambda power n minus 1 into determinant A into A inverse. Determinant A into A inverse is nothing but adjugate of A. So this is equal to lambda power n minus 1 into adjugate of A. Adjugate of lambda A is equal to lambda power n minus 1 into adjugate of A. The next result we are asked to prove is that A is not singular square matrix of order n. Then adjugate of adjugate A equal to determinant A the whole power n minus 1 the whole square. Now, we are already seen from the result 3, adjugate of adjugate A is equal to determinant A the whole power n minus 2 into determinant A. From this, you just take the determinant again, taking determinant on both sides. Taking determinant on both sides. from 3, adjugate of A equal to determinant A in power n minus 2 into A. We already know this result. So in this, if we take determinant on both sides, we are going to get determinant of adjugate A is equal to determinant A the whole power n minus 2 into A. So this is equal to determinant of adjugate A is equal to determinant A the whole power n minus 2 into determinant A. So this is equal to determinant A the whole power n minus 2 the whole power n into determinant A. So this will be equal to determinant A the whole power n into n minus 2 into determinant A. So this is equal to determinant A power n square minus 2n into determinant A. This is equal to determinant A the whole power n square minus 2n plus 1. This is equal to determinant A the whole power n minus 1 the whole square. Therefore, adjugate A is equal to adjugate A is equal to determinant A the whole power n minus 2 the n minus 1 the whole square. The value of adjugate A is equal to determinant A power n minus 1 the whole square. If A is a non-singular matrix, then adjoint of A transpose is equal to adjoint of A transpose. We know that A inverse is equal to 1 by determinant A into adjugate of A. From here, adjugate of A is equal to determinant A into A inverse. Replacing A by A transpose, we get adjugate of A transpose is equal to determinant A transpose into A transpose the whole inverse. Now, the determinant value of A transpose is equal to the determinant value of A. Hence, this can be written as adjugate of A transpose is equal to determinant A into A transpose the whole inverse. So this is equal to determinant A into, this can be written as A inverse the whole transpose. So this is equal to A determinant A into A inverse the whole transpose. So determinant A into A inverse is nothing but adjugate of A. So this is equal to adjugate of A the whole transpose. We have proved A adjugate of A transpose is equal to adjugate of A the whole transpose. So here determinant A being a constant, we can take this transpose totally outside. So determinant A into A inverse the transpose can be written as determinant A into A inverse the whole transpose. If A and B are any two non-singular square matrices of order n, then adjugate of AB is equal to adjugate of B into adjugate of A. We know that adjugate of A is equal to determinant A into A inverse. Now replacing A by AB, we get adjugate of AB is equal to determinant AB into AB the whole inverse. We know that AB the whole inverse is equal to B inverse A inverse. Hence, adjugate of AB is equal to determinant A into determinant B into B inverse A inverse. This can be rewritten as determinant A into A inverse into determinant B into B inverse. By associative law, this can be grouped. Determinant A into A inverse, determinant B into B inverse. So this is nothing but adjugate A into adjugate. So adjugate AB is equal to